All right, conservation of energy. Uh, there are actually a few different ways of stating it. The most common statement is that energy is neither created nor destroyed, but moves from one place or form to another. All right, textbooks state this in a lot of different ways. Mathematically, one way of stating it is delta E of the system is equal to zero, is equal to the change in kinetic energy, plus the change in gravitational potential energy, plus the change in elastic potential energy, plus potentially a number of other terms representing other forms of energy. There is another way of thinking about it, which is that the change in energy is equal to the work external is equal to the change in kinetic energy plus the change in gravitational potential energy plus the elastic potential energy plus any other terms. I tend to take a view closer to the second one, although both are kind of the truth. I should probably note that we have very, very good reason to believe that at least on a local scale, energy is conserved in exactly this way. It can enter or leave the system from outside, but if you have a closed system, the energy of that closed system remains constant. Whether or not it is obeyed on the scale of the entire universe is a little bit harder to pin down. The presence of what appears to be a term we call dark energy suggests that the total energy of the universe may in fact be rising over time, which suggests that there's some really interesting and funky stuff going on at the universal level, but at least on local scales, we believe this to be true and inviolable as you can't violate it as a law. All right, so these are some ways of thinking about it. Here's how we are practically going to use it. We're going to worry about work by external forces plus work done by non-conservative forces, and that will be equal to the change in the energy of the system, which is equal to the change in kinetic energy, plus the change in gravitational potential energy, plus the change in elastic potential energy. These terms right here are sometimes thought of as total mechanical energy. All right, now I'm going to omit the delta E. So work external, which may have to be done as an integral. Work non-conservative, that is usually friction forces. We could treat them as external. I tend to break them out as their own thing, partly because the energy can actually stay inside the system. And it would stay inside the system as the temperature of the system. If you rub your hands together, your hands get hot. Well, your two hands could be the system. So you're doing mechanical work and the energy of the system is actually rising, but it's rising as thermal energy and not some potential energy term like we're used to. Okay, and that would be equal to the change in kinetic energy plus the change in gravitational potential energy plus the change in elastic potential energy. I take this as the master equation for energy. And when I'm solving energy problems, I'll be examining to look at, does the kinetic energy change at all, or is the velocity constant? Velocity is constant, I drop the term. I look, does this change in elevation? If it changes in elevation, I keep the potential energy term for gravitation, otherwise I get rid of it. Are there elastic elements in the system? If there are, I keep delta U. If not, I cross it out. Then I look for resistive forces, things like friction, air resistance, different things we've talked about. If they're present, I'll keep the work non-conservative and figure out how to calculate it. Otherwise, it gets set to zero. I look for, are there external forces that can do work on the system? If there are, I'll keep the work external term. If not, I'll cross it out. The whole process of doing this is just to cross out what you don't need. Then the stuff you do need, draw a picture of the initial state, draw a picture of the final state, figure out how that affects each of the terms. Particularly, we're looking for kinetic energy initial and final, gravitational potential energy initial and final, elastic potential energy initial and final. Additionally, sometimes you will need to look at 3 different pictures and look at how the energy changes from initial to middle, and then middle to final. In cases where you have to do that, initial and final are relatively obvious in the first case. In the second case, what was your final, what happens at the middle position, becomes your initial, and then you get the actual final state. So there are a number of things to consider here. Let me summarize some of what I've just said, though. First, identify and cross out any terms you don't need. Next, draw initial and final pictures and identify things like KE initial, KE final, UG initial, UG final, UE initial, UE final. Okay. Then set up the energy equation and solve it. In some cases, you may have an initial, a middle, and a final state to consider. When this happens, remember the end state of I to M will be the initial state of M to F. Okay. From here, you really need to see example problems to see how all of this is being used. If I have time, I'll try and record them for this, the spring semester of, the fall semester of 2021. If you are taking one of my classes after that point, videos will probably already be recorded for that, so make sure you watch the examples. That's going to be it for this, and kind of it for energy. Up next is just power, if you haven't already done it. My classes do slightly different things. It's kind of awkward recording these videos for both.